Viewers, welcome to my channel, Mugambe Brian 256. So today we are going to continue with how we can determine the specific heat capacity of a solid, and then we are going to use this calculation here. So we have a metal of mass 0.2 kilograms at 100 degrees Celsius is dropped into 0.08 kilograms of water at 15 degrees Celsius contained in a calorimeter of mass 0.12 kilograms and specific heat capacity 400 joules per kilogram per Kelvin. The final temperature reached is 35 degrees Celsius. Determine the specific heat capacity of the solid. So here we are trying to summarize the question. So M subscript M is trying to represent the mass of the metal, and then theta 1 is at the temperature that metal is at. Then M subscript W is basically the mass of water, and then CW subscript W is basically the specific heat capacity of water. Then MC is the mass of the calorimeter. CC is going to represent the specific heat capacity of the calorimeter, and theta 3 is going to represent the final temperature of the mixture. Then using our expression that the heat that is lost by the metal is going to equal to the heat that is gained by the water and the heat gained by the calorimeter. So here basically what we are going to do in our task is basically to notice the temperature changes in this particular case. So when you try to substitute for the temperature differences, so the metal here, it came at relatively higher temperatures, which is theta 1, and it is 100 degrees Celsius. So the final temperature that it will be at is theta 3, which is the 35 upon substitution. So when you go to the water, at first now water was at relatively low temperatures, which was theta 2, but now the final temperature of water is 35. Remember at first it was at 15, so the temperature difference would be the theta 3 minus the theta 2. Then when you look at the calorimeter, its temperature difference, actually its temperature difference will be the same as that of water, reason being they are together. Okay, so they will share the same temperature difference. Well, when you come and substituting, we have the mass of the metal, it is here, which is 0.2. So the specific heat capacity of the metal is the one that you're trying to look for. Then the temperature difference, so it's at first it was at 100 degrees Celsius, then it dropped, its temperature dropped up to 35 degrees Celsius. Then when you go to the mass of water, which was 0.08, then the specific heat capacity of water is basically a constant. Well, it was not given in the question, but it should come to our knowledge that it is a constant, which is 4,200 joules per kilogram per Kelvin. Then the temperature difference would basically be the final temperature of the mixture minus its initial temperature, which was 15. Then when you go to the calorimeter itself, so its mass was 0.12 times its specific heat capacity. Now these ones were given, the specific heat capacity of the calorimeter was given. Then the temperature difference would be basically the final temperature of the mixture minus its initial temperature. So water and the calorimeter were sharing the same initial temperatures. So after substitution and then summing up, the right hand side gives us 6,720 plus 960. Then when you add up, it gives us 7,680. Then on the left hand side, the product of 0.2 times what we remain with is 60, is around 65. So 0.2 times 65. So it leaves us with 13. Then Cm, which is basically the specific heat capacity of the metal that you're trying to look for. Then dividing either sides by 13 and also here by 13, it leaves us with the specific heat capacity of this metal being 590.78 joules per kilogram per Kelvin. Okay, let's have also this example. A liquid of mass 200 grams in a calorimeter of, well, there was a typo here. So at this point here, a liquid of mass 200 grams in a calorimeter of specific heat capacity 500 joules per kilogram per Kelvin and mass 1 kilogram is heated such that its temperature changes from 25 degrees Celsius to 50 degrees Celsius. Find the specific heat capacity of the liquid if the heat supplied was 14,000 joules. So here we go. Well, the heat that is being supplied, it should come to our notice that is used first of all to heat both the water and the calorimeter at the same time. And therefore, the heat that is supplied will equal to the heat that is going to be gained by the liquid and the heat that is going to be gained by the calorimeter. And well, the heat that is supplied, we can denote it by H is equal to the mass of the liquid times its specific heat capacity times the temperature difference. Well, plus the mass of the calorimeter times the specific heat capacity of the calorimeter denoted by C subscript C times its temperature difference. Well, we shall go ahead and substitute for the temperature differences. Remember, the calorimeter is going to be heated up to a temperature theta 2. Likewise, the water theta 2. But initially they were at temperatures theta 1 and theta 1 likewise for the calorimeter and the liquid as well. Well, then we can go ahead and substitute. The heat that is being supplied is 14,000. Now the mass of the calorimeter, they told us it is 200 grams, and therefore we need to convert the grams to kilograms by dividing by 1000. Now what we have here, the 200 divided by the 1000, now everything here is going to be in grams times the specific heat capacity of the liquid, then times the temperature difference, which is going to be the 50 degrees minus the 25 degrees, then plus the mass of the calorimeter, which was 1 kilogram. So here in this equation here, so we needed to make sure that we have uniform units, and now the standard units of mass are basically kilograms. So since the mass of the calorimeter has been given in kilograms, we shall leave it the way it is. So it is 1 kilogram times the specific heat capacity of the calorimeter, which is 500 joules per kilogram per Kelvin. Then times the temperature difference, it is going to be the same temperature difference as that of the liquid, which is 50 minus 25 degrees. And therefore, working on the right hand side, 1 times 500 times 50 minus 25 giving us 25 leaves us with 12,500. Then here this will leave us with 0.2 times 25, which is a result that you get here, will leave us with 5 Cl, or say 5 times C subscript L. Then this will equal, on the left hand side we still have the heat that has been supplied, which was 14,000. Then if you are to proceed and then simplify, so we take this other side by subtracting either sides by 12,500. Then 14,000 minus 12,000 minus 12,500 leaves us with 1,500 is equal to 5 C subscript L. So this dividing either sides by 5 leaves us with 1,500 divided by 5. The final answer, C subscript L, which is the specific heat capacity of the liquid, is going to be 1,300 joules per kilogram per Kelvin. Thank you so much for viewing. We meet in the next tutorial.